It looks a little weird, so I just want to go over it with you. It's kind of cool. It's a nice example of modular arithmetic. Now, these are some numerical examples that give you a feel of if p is 5, p minus 1 is certainly 4. And I did all the arithmetic for you. You guys can go through and double check that. And I tried it out for 7, which is also a prime. And also you get p minus 1 right here as well, right? P minus 1 is going on right there too. So it looks like we got the numerical evidence to believe this statement. Now let's move along. It turns out that the congruence version, in my opinion, and according to the author of this textbook, it's easier to rewrite this in this form. Notice that this is just p minus 1 would be the remainder. I'll write REM there, not rapid eye movement, but R stands for remainder. Okay, and so it's sometimes congruence modular arithmetic is called remainder, because this object right here is the remainder, because it's the remainder you get. In other words, you can write p minus 1 factorial is equal to this plus some multiple of p times p minus 1 is the claim. And that's really what this is saying up here also. Okay, so let's get into what's going on here. Now, this looks Wilson-esque, and so we're going to go ahead and use, this is Wilson's theorem right here. Wilson's theorem right here, folks. Wilson's. Let me go ahead. That's Wilson. Well, I've already told you, right? It's Wilson. This part right here is Wilson's theorem. And notice that it works because just p is congruent to 0 mod p trivially, right? P is congruent to 0. And you can think of congruence and equality as roughly the same thing. All right, so p is congruent to 0. And so that's why these statements are equivalent, okay? Now down here, notice that this is also true. We have the very same congruence, but with a different modulus, okay? Notice it was mod p here, now it's p minus 1 down here. Now this is fairly clear if you just rewrite this. Think of factoring out a p minus 1. P minus 1 is present, and on the left-hand side is a factor. So we'll do p minus 1 times the p minus 2 factorial. Okay, and that's the definition of factorial, really, is all I'm doing here. That's p minus 1, and then this is p minus 2. Factorial would be what would happen if you factored p minus 1 out of this. Okay, but now if you bring this to the other side, you would just have, if you bring this to the other side, you would, let me just write this a little neater for you guys, folks. We need some parentheses here, so you got minus 1, right? Okay, and that's clearly congruent to 0 mod p minus 1, right? P minus 1 is a factor. It's understood that this is the modulus, right? And notice I just brought this over, factored out a p minus 1, you get this statement. And so it's clearly a this statement right here is equivalent to this statement right here, right? So the cool thing is that now we have the very same congruence. Again, you have p minus 1 factorial is congruent to p minus 1 in this modulus, and you have the very same thing in this modulus. Notice that p and p minus 1 are relatively prime, okay? So any two consecutive natural numbers are relatively prime, but I'll just write it down here for the sake of clarity here. P minus 1, p minus 1, and y'all, this is just the notation for coprime. P are equal, they have no common factors, right? In plain language, p and p minus 1 have no common factors. It's written like this, equals to 1, right? Okay. Now what happens when you have that going on, if the modulus, this guy right here, they're relatively prime, that means this statement follows, okay? You can multiply, you keep the very same statement and then you just multiply the modulus. That's something that's not hard to see. It's very easy to prove just using basic divisibility, okay? But I'll go ahead and write QED. I won't rewrite this, folks, but we've demonstrated that this is true, and that finishes things. And I do have one more thing to show you here. Let me just go ahead and QED this thing. Quite easily done, right? No, thus we've demonstrated Okay, so there we go. This has been proven. When you combine these two statements, multiply their moduli together, you keep the same statement. Again, it's very basic divisibility is why that holds, and you guys can verify that. Now, I did want to show you one other example with larger. Look, p equals 11. Wow, look at this one. P equals 11, you get the 10 factorial. That's p minus 1. In whammo bammo, you get 10 right there, which is p minus 1, which is consistent. So I checked it out for a couple of, this took longer than the proof actually to verify it arithmetically. But anyway, that completes the proof, and hope you guys enjoy.